Hi, it's time for another math easy solution. To discuss a pretty interesting topic, and that's looking at the sport of baseball and try to answer the question, does the pitcher's mound add speed? So yeah, I was asked this question online by this guy Duncan Smith. So he tweeted, settle a debate, how much velocity does the pitcher's mound add to a pitch? And then 3-guard rotation, tagged me and says, this seems like a problem for math easy solutions to solve in 20 seconds. I'll take a bit longer than that, but nonetheless I'll see what I can find. And I thought it was really interesting. So my initial thoughts was that horizontal velocity wouldn't change, so the speedometer wouldn't record any changes, I think. And then Duncan Smith wondered what value the mound actually adds, if any, just the angle of approach maybe. And then my initial thoughts was, throwing slightly downwards is easier than throwing perfectly flat from my experience too. So that's what I initially thought. So let's just jump right in and see what I could find. And basically, looks like I've been called on to solve some important math problems. Hashtag I'm the hero you deserve. So anyways, first of all, let's go on Wikipedia and see what they say about the baseball mound. If you go look on the baseball field page. So a baseball field, also called a ball field or a baseball diamond, is the field upon which the game of baseball is played. And specifications here is a note, unless otherwise noted, the specifications discussed in this section refer to those described within the official baseball rules under which the Major League Baseball or MLB is played. And here are those stats. So the one I'm interested in is the 60 feet and 6 inches, or 60.5 feet. That's a distance from this rubber there. That's where the rubber, the pitcher's plate, which is on top of the mound, and throws it over to the home plate over there. So if you look what they say about pitcher's mound, so the pitcher's mound in roughly the middle of the square, equidistant between the first and third base. That just means the same distance from here to here. Like those are the same distance. And a few feet closer to home plate than to second plate is a low artificial hill called the pitcher's mound. This is where the pitcher stands when throwing the pitch. Atop the mound is a white rubber slab called the pitcher's plate or pitcher's rubber. It measures 6 inches front to back and 2 feet across, so just a rectangle, the front of which is exactly 60 feet 6 inches from the rear point of home plate. And that's a distance I'll be using later on in my calculations. So, and now the interesting is the top of the rubber is to be no higher than 10 inches above home plate. So yeah, that's almost a foot. That's pretty much the height that the mound gives you. And also interesting side note is from 1903 to 1968, this height limit was set at 15 inches, but what was often slightly higher, sometimes as high as 20 inches, especially for teams that emphasize pitching, such as the Los Angeles Dodgers, who were reputed to have the highest mound in the majors. So yeah, pretty much they had double the height as the legal one now, or the regulation height now. So a pitcher will push off the rubber with his foot in order to gain velocity toward home plate when pitching. In addition, a higher mound generally favors a pitcher with the height advantage. The pitcher gains more leverage and can put more downward velocity on the ball, making it more difficult for the batter to strike the ball squarely with the bat. The lowering of the mound in 1969 was intended to increase batting once again, as pitching had become increasingly dominant, reaching its peak the prior year. And 1968 is known among baseball historians as the year of the pitcher. This restrictive rule apparently did its job, contributing to the hitting surge of modern baseball, although I think they could go with a bit more hitting, even nowadays. So yeah, that pretty much explains why the higher mound is there. It helps the pitcher and has a downward velocity, and they had to actually lower it because it was harder for the batters to strike it. So very, very interesting. And in fact, when I go through my calculations, that's actually what I confirm later on. So now here's a better image of the pitcher's mound right here. And as you see, there's that pitcher's plate, or that rubber there. That's where they start off from, and it's about 10 inches, 10 inches above the ground, or at least above the home plate height. So now, before I look at the calculation, I want to know, how is a pitch velocity measured? And here's a good website, Hardball Times. The physics of radar guns. Here's some radar guns that people can bring. And it states here, the radar gun can only accurately measure pitch velocity from behind the plate. And so radar, going into the article, radar is not actually a word, it is an acronym. It stands for radio detection and ranging. And then it says, which sort of describes how it works. Just like an echo is a sound wave that bounces off something and returns, radar is a radio or electromagnetic wave that does the same thing. Radio waves all travel at the same speed, 186,000 miles per second, which is the speed of light, or about 1 foot in a billionth of a second. So first measure the time for the wave to go from the radar gun to the ball and back, then multiply the time by the speed of the wave to find the distance to the ball and back. Divide by 2 and you have the distance, etc. Actually, the handheld radar guns don't measure distance because all you really expect from them is the speed of the ball. It turns out that the frequency of the waves that return from the ball is slightly different from the frequency of the waves emitted by the gun. This is called the Doppler Effect, the same Doppler as in a weather reporter's Doppler radar. You can hear the Doppler Effect for sound waves if you stand by a busy highway. The sound of a vehicle coming toward you has a higher frequency than it does when it is heading away from you. You can really notice a change just as the vehicle passes, so check that out. Here's a Doppler effect that's used in the radar guns, and one way to see it is if it's just standing still like that. Actually, I forgot to add this text about that article. So this figure, what it is basically saying, let's start to understand a Doppler effect by thinking about that home run ball bobbing up and down in the fountain or just in a pond or water. So if you have a ball, put it up and down, is what happens is each oscillation creates a circular wave that travels away from the ball like that. You could just drop it in a little bucket of water and see what happens like that. But then if you move it across, the waves become, well, it's going to become something like this on this right side, where they get compressed on the as you're moving it towards that area, and then it's wider spread waves on the other side. So the ball is bobbing up and down, creating circular waves that move downward or move outward. The ball is moving toward the right, so the waves in front get squeezed together while the waves behind spread apart. And the way the radar guns work is like this. So the larger wave is sent by the radar gun toward the ball. The larger gray wave. The ball reflects a smaller wave back toward the gun. So when the ball is at rest, the reflected wave has the same frequency as the incoming wave. So here's the ones going this way, and then these go backwards. This is just standing still. But then, like how the ball is moving inside water, this one, as it's moving here, you have the same radio wave coming this way, and then you have a faster frequency because the ball is moving towards the right. So when the ball heads toward the gun, the reflected wave has a higher frequency, like that. And that's pretty much how they measure, and you calibrate it and see what kind of frequencies for whatever speed of the ball is. So basically, the faster the ball, the more radio waves are reflected back, i.e. at a faster rate. And now here, one downside of a basic radar gun is the speed it records is only the part of the speed along the direction you point the gun. This explains why people using radar guns congregate behind home plate. That's the only spot where it measures the correct pitch speed. Alright, so now moving forward, so Statcast. So on opening day of 2015, the next generation of technology was supposed to begin operation in all 30 major league ballparks. The system uses TrackMan to follow the ball through the park, throughout the park. In addition, video technology from Cairo Higo was to monitor the motion of every player at all times. That's pretty amazing. And radar is much better for monitoring the ball because it travels so rapidly. So Statcast system they use. And table 1 summarizes just some of the data that are collected and displayed by Statcast. So only one I'm interested in is pitching. So pitching includes the extension, velocity, spin rate, and pitch types such as fastball, curveball, and other stuff like that. So yeah, interesting stuff like that. An extension here, this one's interesting. So the extension, so a pitcher must begin his throwing motion while standing on the pitching rubber, which is 60 feet 6 inches away from the home plate. This does not mean pitches are actually thrown from that distance. The point at which a pitcher releases the ball is actually a few feet closer to home plate than the pitching rubber itself. Extension quantifies just exactly how much closer a pitcher's release point is to home plate. So taller pitchers with long wingspans tend to have the longest extensions because their frames allow them to hold onto the ball for a greater distance before releasing it. So not surprisingly, a longer extension can be a major advantage to pitchers because they are essentially shortening the distance between themselves and opposing batters. A pitcher with a longer extension can make a 93 mile per hour fastball look like a 96 mile per hour fastball because they release it later, which is quite amazing. In this regard, extension is a key component in the Statcast measurement perceived velocity. Yeah, so here's a Statcast, some of the stats they have. Extension velocity, perceived velocity, here is a bit slower there, and spin rate. And I believe that is the radar gun there, I believe. Yeah, I just drew that in yellow there, so that I believe that is the radar gun. And here I put that note. Notice the location of the radar gun behind the baseball field and between the fans. If I'm mistaken, please let me know. Now if you go to the perceived velocity, this is an interesting part. So perceived velocity is an attempt to quantify how fast a pitch appears to a hitter by factoring the velocity of the pitch and the release point of the pitcher. It takes velocity one step further because a 95 mile per hour fastball will reach a hitter faster if the pitcher releases the ball 7 feet in front of the batter, in front of the rubber, instead of 6. To attain perceived velocity, the average major league extension must first be obtained. Any pitcher who releases the ball from behind the average extension will have a lower perceived velocity than actual velocity. On the other hand, if a pitcher releases the ball from in front of the average extension, so like a tall player with a long reach, he'll have a higher perceived velocity than actual velocity. So that's some background on all this baseball stuff. Now let's use that info and see what calculations we can get. So from what I've read so far, it is not too clear whether the radar measures the horizontal ball velocity, the absolute ball velocity, somewhere in between, slower than the horizontal or faster than the absolute velocity that the ball is moving. But my guess is that the radar reading is slower than the horizontal, or at least more aligned with the horizontal speed and not the absolute speed of the ball. But as I'll show, those don't change too much anyways. Well, there isn't much difference between those. And why I think that is basically, let's say if you have the mound right here, here is the rubber, looks something like this. And let's say you had your home plate across there. So there's the home plate, it's flat like that. Let's say the ball's in the air like this, and it's being thrown downwards like that. Yeah, everything is just exaggerated just to show you. So let's say we had the radar gun, it's somewhere over here, and as you can see here, scroll up to the radar gun, it's not exactly perfectly aligned either. It's not perfectly aligned behind the batter over there. It's somewhere to the left there. It could be behind, so I guess different ones have different locations. So let's say it's going towards it like that, and then what it does is shoots these radio waves across, has the same frequency like that, and hits the ball, and then the ball reflects back depending on the speed that the ball is traveling. Could be, let's say it's gonna be faster rate than the incoming ones like that. Yeah, so as the ball's going downwards here, but the device is somewhere across there, so it's hard to tell whether it's the absolute one, horizontal, or somewhere in between. But again, I believe it won't change much. So yeah, so thus, if the radar gun reads more or less just the pretty much horizontal speeds, increasing the mound height will, in theory, decrease the overall recorded speed. But as I'll show later, none of that changes much anyway. This is, again, without taking into account pitchers' preferences in terms of mound height. Human physiology, i.e., is throwing slightly downward easier than throwing perfectly horizontal? Those are good questions asked. So I'm just going to ignore those and just look at in theory. So now let's take a look at how the absolute velocity changes. So let's say you had our mound look something like this, and there's our rubber, and that's the rubber, and let's say the diamond is somewhere over there. Then we have our pitcher right here, his foot is across there, and then it's let's say the foot, it's leaning towards here, and then there is the arm that it throws it with, and there he is. Now let's say this rubber right here is at a height h, and this reaches just to the top of that. And now let's say the release point is somewhere here, so that means that the extension across from this point, let's say from the front of this one, across from here to here. I'm going to call this X, or EXT, or X. Yeah, for extension. Yeah, so we have that. Now let's say you have the ball in the air like this, and it's going at a velocity v, like that, all the way across, somewhere over there where it's a strike zone. And now let's look at our total distance across from here, the front, to, let's say, somewhere across, yeah, the center one. I'm just going to guess there. And this one, we're going to call this distance d. So that means that the actual distance that the ball is in the air for is going to be from here to here, so d minus x. Alright, so now that we have that set up there, so now to simplify the calculations, I will not take into account the pitcher height or the batter height in the resulting strike zone, just because it's going to get more and more complicated. I'll try to simplify it as much as I can. So I'll instead compare a perfectly horizontal throw versus an angled throw downwards from a mound height of h. Yeah, so if we have a perfectly horizontal throw, what we end up having is, let's say the ball is here, and now I'll just draw a little dot. So let's say initially you have it there, and now you're throwing this perfectly horizontal at a velocity v equals to, I'll call it VO or V naught for initial velocity, and this is just equal to v horizontal, and that is constant. I'm also going to ignore air resistance. Now here I type that out. It also will not account for air resistance. Just again, it adds more complexity, but I believe it wouldn't change much because it's going to apply to both the horizontal and angled throw, so it wouldn't affect either too much when you're looking at a comparison. But yeah, notice that even though you have a perfectly horizontal throw, it's going to sag downwards due to gravity. I'm going to account for that, and the distance from there to home plate is going to be across there. That's going to be our total distance minus the extension, so d minus x, like that. So what we end up having at this point here, we have again that same VH is horizontal, but now we have a downwards force. I'm going to move this down like that. We have a downwards velocity here of v d, like that I'll call it, or vdf for downwards velocity there. Initially here you have vd naught is just equal to 0. It's just perfectly horizontal one. Yeah, and I'm going to write over here, this is constant, like that. So then the absolute velocity, just for completeness sake, is going to be somewhere across there, and that's going to call it v, and I'll call that vf, like that. Yeah, now if we look at a downwards throw, the only difference, now we have, let's say, a height from here to here. This is going to be the height of the mound. That's going to call that h, and now we're throwing it at an angle downwards v. And again, the full distance, I'm going to call this v naught, and it's not going to be the horizontal. And again, this distance is just our d minus x. And then similar to this one, we're going to have a vd0, but it's not going to be equal to 0 because it's a downwards velocity as well. But before I get to that, I'm going to assume that this angle of this velocity across like that is going to be all the way across here. This is going to be, I'm going to assume this is a angle theta, like that, and there's the height. We have a right angle triangle like that. And the reason I have that angle is I'm going to assume that's the exact angle that we're going to throw it with initially, and again there's our vd0, like that. So let's draw that out. So at the point of release, the velocity of the ball can be visualized as, let's say you have the ball right here. This is at the time is 0, like that, and now we have it going this way at a velocity v0, and now we have a downwards one vd0, I mean v not d there, and then it has a horizontal component. I'm going to call this vh, and this is constant because there's no other force acting on it. It's only going to be gravity acting on it because we're going to ignore air resistance. So vh is constant, like that. Yeah, so for both the horizontal throw and the downwards one, we have a horizontal one that's constant, but initially our throw is going to be downwards, like that. Now we're going to assume that this angle is the exact same one across there, theta. So then the tangent of theta, just recall some trigonometry. I'll put the links in the description below if you haven't already caught up to trigonometry. So the tangent here is going to be, well, h over, or opposite over adjacent, so h over d minus x. That's how you can get the angle there. And now this means that we can write this right here as the opposite over adjacent, this equals to v d0 over vh, like that. Yeah, so then we can solve for the downwards velocity, because we're going to have to put all these in a giant Excel sheet later on. So what we'll do is we can just move this over to that side. We get v d0, the initial downwards velocity, is equal to h minus d minus x times by vh, and I will circle this like that. And now also recall Pythagoras. Yeah, so I'll write that as recall the Pythagorean theorem. So and write that here. So Pythagorean theorem. So then we have this velocity like that, v0 squared equals to the square of the other two, so v d0 squared plus vh squared, like that. The reason we're doing this is the only one we know is this one. We're going to assume we are given the v0, that's the velocity we throw at initially, and see how it changes. And then to get the downwards one, we need to know what this horizontal one is in terms of the v naught or v0. So we can throw this inside there. So just put that inside there, and then if we plug that in, we get this h. I'll just put that over here. So we're going to have an h squared over d minus x squared, and then times it by v h squared, like that, and then we have this part there, vh squared. So now we could just factor that vh squared out, so we get a v naught squared equals to a h squared over d minus x squared plus 1, just factor it out, vh squared, like that. And then divide this out over there, so we get a vh squared equals to a v naught squared over now we have like here, h squared over d minus x squared plus 1. And then what we can do is just factor both sides, so what we end up getting is a vh equals to, well, it's a plus or minus technically, because inside anything could be plus or minus, but we're only going to look at the positive one, otherwise it wouldn't make sense for negative velocities in this case. So we're only looking for the absolute, so it's going to be just plus, and then we have a, well, this one just cancels, so that just goes v naught like that, divided by then the square roots at the whole bottom. So we have h squared d minus x squared plus 1. Yeah, so that is our horizontal velocity based on the known velocity that we're throwing it at. See how it changes. We could get the downwards velocity there initial as well. And again, as explained before, so when the ball reaches the home plate, the downward velocity and absolute velocity increases, but the horizontal velocity remains constant because there was no force pushing it forwards. So what we end up getting is, if this is the initial one, all the way till just above the home plate, like that. Here, just above it, we have the ball like this. And now its velocity is changed here. We have a v, I'll call this vf, that's the absolute one, and then I'll move this downwards more so. So we have here the velocity of v df, the final downwards velocity, once it reaches the home plates of v df. But again, the horizontal one is going to be constant. That is vh, still the same as before, the horizontal component of the velocity. So again, when the ball is in the air, ignoring air resistance, the only force on the ball is just gravity, which is a downwards force. Yeah, so we have the ball in the air like this. The only thing acting on it, that's a force. A velocity is not a force, that's just the ball moving. Like air resistance would be considered a force because it's slowing it down. So force is just equals to mass times gravity. And this is just constant. The mass is constant, the gravity is constant as well. So as it's moving downwards, the only thing acting on it that is going to change its speed is downwards one, like that, and that's just going across there. And now the gravity, acceleration due to gravity, this is just, again, constant. It's in meters per second, 9.81 meters per second squared. And then this is constant. You could also see this, can view this as the rate change of the velocity, or the derivative of velocity dv over dt. And now we're going to do some calculus and do some implicit differentiation. Implicit integration. Actually, I think I got that term wrong, a bit mistaken. I'm just going to move this over there and take the integral on both sides. So we have dv equals to now g dt. So again, if you remember your calculus, take the integral on both sides. Then what we end up getting is, here I want to make another note. Since we're only dealing with downwards, I'm going to call this dvd for downwards there. So then the integral of this dvd, that's just going to be velocity like that, equals to g times integral of g is just a constant, so we can put a t there, and then plus a constant c like that. So at now t at the time is equal to 0, what we end up getting is vd of 0. This is going to call this vd initial like that. That's just going to be, well, g times 0 is 0. Like that. It's just going to be 0 plus c. I'll just ignore it. So this is just going to be equals to c. And then, yeah, so that's what we have right there. vd0 is equal to c. So thus what we have is the downwards velocity as a function of time equals to gt plus vd0, where we already know what vd0 is. This one is based on the horizontal one, which we know, and that's based on, so we can solve this one because we can solve this horizontal velocity because we know v0, or the velocity you throw at. And now to solve the velocity at the final time when it reaches home plate, I'm going to call this at t equals to t final, where it reaches home plate. This just equals to vd tf, which I'll call this one vdf like that, equals to g, and then just to tf, we just plug that in over there, vd0. So what now we need to solve is this tf. And now to solve for that tf, note that while the horizontal velocity is constant, equals constant, we know it, we can solve it given v naught or v initial. So this means, yeah, it's constant. Also, we know that the velocity is just distance over time. So then what we could do is, well, the overall distance d minus x. So thus we have a constant one like that, vh equals to d minus x. That's distance. To travel that one, we're going to have to travel it in a, I'll call this delta t, the change in time, and that's d minus x over, we know this one right here. This is just going to be t final minus t initial, which is, well, 0 seconds, I'm going to call it. So initially we have t0, so tf minus t0, that's just tf. Like that. So we can solve this, and we get tf equals to, move that over and divide it out, d minus x over vh, like that. So we have this, and we can throw that inside above there. Yeah, so thus what we end up having is, we put these all together, thus the one we know, will assume that v naught is given. So we know this. So from here, it's given, we can solve vh, that's a horizontal constant velocity, and we can scroll up to solve that one. Vh is over here, v naught over square root h squared divided by t minus x squared. So this equals to v naught over square root, this is going to be h squared over d minus x squared plus 1. And then the vd naught, or the initial downwards velocity, we can solve this. This one, well, we already have that. Let's go up here. That's going to be based on our horizontal velocity. So that's h over d minus x vh, like that. So we have, this is going to be h over, d minus x, and then this is going to be our vh, like that. So we get from here to here to here, and then the next one we got to solve this time f, like that. So vtf, actually it's not vtf, this is just tf, so we don't know this tf right here. That is, the next one is this one right above, above here. So that's this velocity, or the time there. So that's dx, d minus x over vh, like that. So we have this one, and then finally the downwards velocity vdf final. This equals to gtf plus vd d naught, like that. And that's this one right here. Yes, we have that, and also finally, and what we have is, recall, just using the Pythagorean theorem again, we had the ball like this for any, let's say any velocity like that, v, yeah, I'll just call that v like that, and then we have this one is our, I'll put it over here, downwards one v d, and then the horizontal one vh. So then we can solve this v1, so v squared equals to vd squared plus vh squared, like that, square root both sides, plus or minus, and then just becomes plus, like that. So, and this one, recall that, so then we could throw that above and use that for our initial and final. So then the absolute velocity v naught equals to, the initial one is just going to be, well, just use the initial values, vd0 squared plus v, this is vh is constant always, and not just squared, and then vf final, this is just going to be vdf downwards velocity final, like that, squared plus vh squared, like that. Yeah, so now we have all these equations finally set up, and then we put that all in a calculator. Yeah, so I put these all in the calculator here. So I've created an Excel sheet to see what kind of numbers we get, and you can download it from this link. I'll also put that in a link in the description below, and download and play around with it, and let me know if you see any mistakes that I made. And then what we end up getting here, I'm going to use gravity 9.81 meters per second squared. And now here, the initial throw velocity, or the throw velocity, throwing it as v0, and then it gets affected by gravity, etc. So we have the mound height h, extension x, time to reach home plate tf, ball velocity at home plate vf, and then gravity g, it's 9.81 meters per second, and then the distance between rubber and home plate, to call that d. So here's it is for different values of h, here for a perfectly flat d, and then we have the height is 10, that's the requirements now, the maximum height, and this was the previous one, and also I believe they could get away with 20 inches height, like that. And I use extension, all of these is 6.5, all these is 60.5, the distance from rubber to home plate. And I use the initial velocity, everyone throwing 100 miles an hour. What we notice is the time that it reaches to a home plate, 0.368, all of them pretty much about the exact same. This one's, again, because it's higher height, it can be a slightly different distance. So then there's going to be like a tiny difference across here. Basically, to 3 decimal places, it's all exact, and then afterwards it gets a bit iffy. And now you can see that the horizontal velocity, again, if you're throwing it perfectly flat, that is going to be your initial velocity, is going to be your horizontal velocity, 100 miles an hour. The downwards one initial is 0, but then after 60.5 feet, well, minus 6.5, because we need d minus x, we get an 8 miles per hour downwards velocity. That's very interesting. And then the absolute velocity is just above 100. Again, this 0.3 or 0.3% increase, very minimal in my opinion. And then when you raise it to 10, there's the mound, the regular one. It's a slower, tiny bit slower velocity horizontal, as I predicted or stated above. But again, barely any, 99.98. This one's 9.5. That's because it's 20 inches above. And then, yeah, so as you increase the height, the absolute velocity, this one's only by 0.1 difference, and then 0.1 again, so absolute minimal there. The only one I see is this downwards velocity. You're going from 8 to 9.6. This is the old, this is the current one, so you're literally increasing by about 1.6 miles per hour. That is a big time increase. And then here, when it was at 20, you're going to a 3, almost 3.2 miles an hour difference downwards velocity. That's actually quite amazing in my opinion, especially when you look at it with thousands of pitches across many games. It's going to be a big factor in who wins and who loses. Yeah, so thus it appears that the horizontal velocity decreases as you increase the amount. Yeah, so horizontal decreases barely. Again, these are just like minimal at best. So the absolute velocity increases, again, not Yeah, not by much. If you go from 0 to 20, which is again, that's not even legal now, that was only 0.3 miles per hour difference. But the only one big one is that downwards velocity increases approximately 1.6 miles per hour every 10 inches the mound is raised. That's quite amazing. So thus ignoring any pitching mechanics that affect angles of fastest throwing speed. Yeah, so any mechanics of how you actually throw, if it's throwing downwards easier, etc. I'm gonna ignore that. It appears that the radar gun readings will likely not be affected by the mound height, because as you can see here, the absolute velocity is not changing much. The horizontal one is not decreasing by much. And already the radar gun, it's iffy on what exactly it's measuring, so it seems like just a merger of all absolute and horizontal. But nonetheless, the higher the mound, the higher the downward velocity, again, and also the more angled throw, and the harder it is for the batter to hit the ball squarely, and this helps explain why 1968, the year before the mound height was lowered, is known as the year of the pitcher. Anyways, that's all for today. Yeah, play around with that Excel sheet. Let me know if I made any mistakes, or if you can expand on it and test out different variables, such as different initial velocities, and also different extensions here for taller players, shorter players, and whatnot. Anyways, that's all for today. If you learned from this extensive baseball physics and calculus lesson, and also some radar info and some background on it's very interesting stuff, the statistics behind it. But at the end of the day, the mound is pretty much downward velocity, and the angle. Yeah, so that just increases the downward velocity. But radar gun's not going to change much, in my opinion. And that's all for today. Hopefully this answers your question, Duncan. Anyway, that's all for today. Hopefully you learned. Like always, you can download these exact notes in the link below, as well as viewing these notes in article format on Steemit. Yes, follow me at MES. Anyways, that's all for today, and thanks for watching, and stay tuned for another Math Easy solution.